All right, should be recording. So this week we're going to be talking about controls and the use of controls in robotics. We're going to start off with a very high level overview with these lovely little block diagrams of what it means to control a system, and in general what it even means to have a system. So in a very abstract sense, a system is something that has some memory, and you put inputs into it, right? And those inputs are like the voltages that you might give to a motor, or they could be torques, right? Some sort of way that you change what's happening in the system, and also some output from the system that you then later measure, right? And that's going to be like your sensors. So we give each of these letters. We have inputs, which are U, outputs, outputs are Y, and then we have this thing called internal state, which is X. And internal state is what's actually happening within it. So I'll give you some more concrete examples so that this makes a little bit more sense. But internal state would be all of the variables that you need to predict what the system is going to do next. So for example, it might be the position and velocity of a robot, right? And we talked, I think, a little bit about that in last week's motion planning lecture. So an example of this is, it comes from a competition that is very near and dear to my heart, FRC, which was how I spent like all of my time in high school. But if you are not familiar, a very common mechanism in that robotics competition is a shooter wheel, where you basically just have a bunch of motors strapped to a wheel to spin it at a very high RPM and shoot out a ball or something like that, right? And in general, you can sort of just apply that framework that we've got from here to this system, right? We've got inputs. We have motor voltages that we need to apply across the motors, and that's what actually causes them to turn, right? We've got outputs. We've got some sort of sensor. If you remember encoders from the second week, you'll often have an encoder on the shaft of that motor so that you can tell how fast it's spinning. And then also you've got state. And in this case, you'll notice that state is velocity, right? So state is just how fast the wheel is spinning. And if you know how fast the wheel is spinning and what your voltage is, right, what voltage you're giving to it, you'll know how fast it's spinning in a second from now, right? Or you can predict that. So in general, that's what we mean by state, right? All the things other than the input that you will use to actually predict the future. As a note here, for the remainder of this presentation, I'm going to try to say control input or sensor output rather than just input or output. I find that the terms input and output can be really confusing because you usually think of things from the other perspective, from the perspective where sensors are inputs to your code and the outputs are motor voltages. So I'm going to try to say control input. See, I'm doing it already. Control input for actuators, right? And then sensor output for any sort of sensors that you've got. All right, another very common system that's a little bit more complex now is a differential drive, right? And a differential drive is where you've got two wheels, one on the right side and one on the left side. This is what IGBC uses, actually. Sorry, the IGBC robot. The RoboNav in general uses this. And you've got two independent motors controlling those two wheels. And when those motors are both going forward, your robot will go forward. When one motor goes forward and one motor goes back, your robot will turn, right, in place. And then when one motor goes at a slower speed than the other motor, it will sort of arc, right? So this is the case where it's going straight. This is the case where it's arcing, and this is the case where it's turning in place, right? Those are sort of three different variants of actions that you can take with this type of drivetrain. And in general, what your system or what your state is sort of depends on what you're caring about. You could make a sort of subset model, right? A model that sort of only encapsulates certain parts of it that would just be velocities, right? If you only cared about the velocity of your drivetrain, you could make a model for it that was just containing the velocities of the wheels. However, often in all of our competitions, right, we care about position and velocity. We care about X, position, Y position, the heading of the robot, and the velocities of the wheels, right? And together, all of those variables are able to describe the state or how this is basically the current motion of this robot, right? Similarly to last time, our inputs are motor voltages, right? We just apply some voltage across the motors and they turn. So that's relatively straightforward. And then our outputs are a lot more complex this time. So we do have measurements of the left and right wheel encoders, right? Those are direct measurements on certain parts of the state. But we also have a lot of other sensor outputs that are giving us information about the state of the drivetrain, right? And you can think of these as like gyroscopes. So those also give us like angular velocity, right? Which tells us something about these left and right velocities. And then we also have things that like camera and LiDAR that give us very indirect measurements of where we are in the world, right? But those do allow us to compute a more refined estimate of those things. Yeah. Big thing to note here is that unlike a lot of other things, this has a constraint where it can't move sideways, right? So if you try to take Jesse and you try to push the robot sideways, that's the IGBC robot, you just try to push the robot sideways, well, you might be able to push it sideways, but the robot can't actuate itself sideways, right? So there's a constraint on the motions that you are able to perform. And then finally, one more example from Robocup is just the Robocup robots. Basically, they don't have that constraint. Robocup robots are, because they have these wheels within wheels, they're called omnidirectional wheels, and they're basically just able to slide sideways. We're able to, by varying the combinations of motor velocities, you're able to move sideways across the ground, right? So Robocup has a very different set of constraints on its controls or on its system, right? On how it can control its system specifically than IGBC. So yeah, it's got 4-wheel motors, you can move in any direction. And something big to note here is that the wheels can slip, which makes this a much more complicated system to deal with, right? So if you're actually dealing with the sort of naive system, quote unquote, where the wheels don't slip, your state is XY heading, XY velocity, and angular velocity. It's basically the same, pretty much the same as for the IGBC robot, with the exception that you can now move sideways. If you do include wheels in this, right, wheels slipping, your state is actually that plus the velocities of all the wheels, which is much more complicated and much more difficult to understand the dynamics of. And then inputs, I think these should be pretty familiar by now. Control inputs are motor voltages, sensor outputs are gyros, accelerometers, wheel encoders, etc. Okay, so I just spammed a lot of information at you, and none of it was really intended as information that you need to know. It was sort of background information on what a system might look like, right? But it doesn't necessarily tell you anything about controls in and of itself. And you would be forgiven for, thinking, Kyle, why did I just spend 10 minutes listening to you not talk about controls? So the idea, or the important part, is that we need to understand our system in order to actually control that system, right? And we define controls as how we calculate the inputs to the system. So how we calculate those control inputs, those motor voltages or motor torques, or however we control our system, how we actually calculate those. And often you'll find that we calculate those using some combination of the state of the system, right? Or the outputs, the sensor outputs of a system, right? Those all provide very common ways to control systems. So we're going to build up a controller from the most simple possible mechanism or algorithm for control that you could possibly think of. And the most simple algorithm that you could think of is just if you want the shooter wheel to spin at 100 RPM, test a bunch of voltages when you're designing things, figure out which one gives it 100 RPM, and just give it that voltage, right? Which isn't entirely awful. This can work for certain. This is also known as like dead reckoning, right? You might have heard that term before. And it can work for some things. In general, though, it's going to suffer from some error, right? And that error is if conditions aren't exactly the same when you are running it as when you were originally testing it, it's going to do something very different, right? In general, this can be acceptable in some cases. For example, if you have a shooter wheel, spinning it at full voltage might just be good enough, right? But if you're trying to drive in a precise motion, dead reckoning is probably not going to be repeatable, right? One time you might end up, in one place. The next time you might end up 3 feet to the left, just because you tried to drive and you hit a bump somewhere along the road, right? So in general, open loop control kind of sucks at dealing with anything where you might have either disturbances or differences in your test setup from your actual run setup, right? This can also include like battery voltage changes. If your battery is a little bit less charged, you're just never going to be perfect. So if the system doesn't do what we expect, it has problems, right? If we try to use multiple robots, we're going to have problems, or at least we're going to have to change all of our controllers, and that's going to be a lot of work for us, which we don't want to do. This one is particularly important for Robocup. If we have different ground conditions between test runs, that can change things, right? IGBC doesn't always have the same ground, so you can't just, you can't just run the IGBC, the entire IGBC competition by recording one good run of it done by a joystick and then, playing it back. That's not going to work very well because things are going to change. So in general, you're going to have things that you just can't predict. And for your purposes, they're going to be random, right? Because you can't predict, even if they're not actually random, even if we live in a perfectly deterministic universe, you just can't model enough complexity to account for all of them. And so they're essentially going to be random. And here we've got some visuals of what might happen to an open loop controller if you try to, just run it in open loop. You could, so if this blue is our set point, that's what we're trying to get to, say it's a velocity that we're trying to get to, you might have things that converge a little bit lower and never quite reach it. You might have things that converge right at the target. Or you might have situations that just never converge and overshoot it and never come back down. Right? And these are all cases that you'll see when you try to run open loop control. So that sucks. We're going to try to do something better. And from there we come to this concept of a closed loop controller, which is something that uses the outputs of the system, the sensor outputs, right, in some way to calculate the inputs. The control inputs, right? And in a sense, our entire robot code is a big closed loop controller. You can view it like that if you really want to. But we usually like to zero in on certain parts of that, and we like to separate things out. So a lot of the time, we will separate the whole autonomy stack, right, into a couple of different things. We'll have perception, right, which is where we perceive the world, use computer vision and whatnot to figure out what's going on in the world. We'll have some notion of motion planning, and that sort of is what generates a trajectory for us to follow. And then we'll have some notion of motion control, right? And all motion control does in this paradigm, and this is the paradigm that I'm going to be using for the rest of this presentation and talking about for the rest of the presentation. All that motion control does is it takes as an input the state, right, or some estimation of the state, right, some estimate of the state. So we might, given all of our camera information and our encoders and all the information that we have available, our GPS and stuff, we might say, okay, I estimate that I am here and I want to be here. How do I make that happen? All right, so you have a state and a goal state. So really, I guess this should be saying, for most of the way that we're going to use it, a closed loop controller uses the state of the system to calculate the inputs. So we just got done with looking at the dumbest possible control scheme. Let's look at a step up from that, we'll say. It's not completely dumb, it does have some sort of feedback and it's able to hit the target, but it's not great. So the idea is it's called something called bang bang control. And the idea is that we apply full output whenever we are below the target and zero output or negative full output whenever we're above the target, right? So we just pick a target. Whenever the output is less than reference, you give maximum control input. And whenever output is more than reference, you give minimum control input. And the idea is that if you repeat this quickly enough, right, if you do this in a loop, in a very tight loop, hundreds of times per second, you might get something reasonable, right? You're going to be switching between full and negative full or maximum and minimum control input a lot. But in theory, it should sort of balance out to give something that just sort of tracks at the goal. So this has some good things and it has some problems. The good thing is that it is, in theory, the fastest possible way to get to the goal, right? It should be almost perfect, right? To actually get to the goal. However, once it's at the goal, it's probably going to actually overshoot the goal. And that's a very common thing to happen in when you're actually trying to use bang bang, right? And if you want to think about why this happens, well, think about a block just a very common example in control systems is a block sliding along the ground with no friction, right? And you can apply a force, that's your control input to the block. You can push it, and that allows you to manipulate where it is, right? And you're trying to get it to a target position. Well, if you use bang bang on that, you're going to continue to accelerate it really hard, right? Until it passes the center line or wherever you actually want to get it to, right? And it's still going to have velocity at that point, and you can't instantaneously stop it. So at that point, you're just going to start trying to slow it down. Then you're going to be still way far past it, right? So you're going to go the other way and you're going to overshoot again, right? And this is sort of a fundamental issue with bang bang. It is very likely to overshoot, and if you're particularly mathematically inclined, you could say that it doesn't work well for systems that aren't of first order, which is not a Star Wars joke. It's just saying that like any system where you're commanding, for example, something that influences acceleration, and you're trying to control two derivatives down from that. So trying to control position using acceleration. Bang bang is just going to go all over the place. It's going to overshoot the target, and it's going to be garbage. So bang bang is not great. What can we do to fix this? And again, the idea is that so it works poorly when the output lags behind your controls, right? So position lags behind velocity, or when you control a system very slow. And it's also not great if you try to run this on a robot. Mechanical will definitely yell at you. So we want to not have this, and we want to actually have some smaller control input, right? When we get very close to the target, right? So we sort of want to have maximum control input when we're far away, and then smaller control input when we're actually close to the target, right? And if we do that, we might be able to get some sort of smoother controller, right? That doesn't have this major overshooting issue. So the way we do this is we can define error as our goal, or you might hear me say reference, right? Our reference state minus our actual state. And we want to apply more control effort when we're far away from that, and less control effort when we're really close to it, right? So, if my goal is to hit 1,000 RPMs, right? And I'm at 0 RPM, I should give full voltage. If my goal is 1,000 RPM and I'm at 999 RPM, I should probably give something much, much smaller than that, right? And we shape this by, in the simplest possible way, we pick something very simple that we can use. We calculate control input as some constant times the error, right? It's just proportional to the error, right? And we call this proportional control. And you'll see this constant Kp pop up. So we still have to actually pick this constant Kp, right? But and you can see the graphs on the right, what the value of KP is does drastically change what you'll do, right? For a super high value of KP, well, if I have, KP is 1,000,000, even if I'm at 999 and I want to be at 1,000, I'm still going to be giving, I guess, 1,000,000, right? Whereas if KP is like 0.01, I'm going to be giving substantially less at that point. So it's a balancing act, right? Yeah, so somebody asked, what is KP? KP is an arbitrary constant that you pick. So it's called the proportional constant, which is why, like, K is usually named, K is usually like the name for constants, right? P stands for proportional. And it is just an arbitrary constant that you pick, right? I forgot to put a formula on this. Well, I guess this is the formula, but I didn't format it nicely using LaTeX. So your input, remember you would write your input as U, your control input, your voltages or whatever they are. You just say, you make this function, right? And this is how you're going to define your control law, right? And you say your controller is that your input is always some constant multiplied by the error between where you want to be and where you are, right? So it's what you multiply by the error to get the control input. So in general, there are some like rules of thumbs written on the slide. Rules of thumb. For high KP, right, it's going to converge very quickly. But if your KP is too high, it's going to jump around the target, right? It's going to overshoot, and then it's going to come back, and you're going to see this behavior right here. So I've got a couple illustrations of what can happen with different constants of P, right, or with different systems. I don't actually have this. Yes, I do actually have it written out. Excellent. Okay, cool. So the first question is, what if we still need to apply some control input to stay at the goal? So if when we are at the goal, right, we need to give some additional torque, right? So like the example of this, and I keep coming back to the shooter wheel because it's a very simple system, right? It's just a wheel attached to a motor. But in that case, right, if you don't apply any voltage or if you stop applying voltage, the wheel will eventually spin down to zero, right? It'll stop spinning. So what is proportional control going to do when you are at the goal? Can somebody shout it out or put it in the comment section? Let's try to make this somewhat interactive. If you are at the goal, so if your error is 0, what is your output of your proportional controller going to look like? Yep. So somebody just said 0, right? Which means that in practice with proportional controllers, if you're in such a situation where you need to have some additional power when you're at the goal, right, to maintain in the same position or the same state, right, the same velocity in this case, you're going to see something that looks like this red curve, where it's exponentially and it's asymptotically approaching some value that's less than the actual goal. The goal's in purple here. What you actually want to happen is something like the green curve, right? And then just another comment is that if your proportional is too high, right, you can have this situation where you apply too much power and then you have too much velocity, and for right up until this point, right, where you actually cross the goal, you're going to be still giving it more power, right? You're going to be pushing it harder and harder. So in that case, you actually want to push it above the goal, or sorry, you're going to push it above the goal, right? And then you're going to have some counterbalancing force that you're going to push it in the opposite direction because it's going to be too high, and your error is going to be I guess your error is going to be negative rather than positive, right? So you're going to push it in the other direction, but like you're going to have this overshooting behavior where you go past the goal. So these are just all things to keep in mind when you're tuning controllers, and we're about to address them all. The first thing that we talked about was this idea when we need to apply some control input to stay at the goal. So we're going to address that with something called integral. So hopefully you guys have taken a calculus class and the term integral is not foreign to you. But the idea is that we are basically just, if you don't like the term integral, it doesn't matter. We're just going to delete it and actually just call it like, we're actually going to implement this in practice by summing things up, because our computers don't run infinitely quickly, so you can't actually take an integral. But the idea is, if the errors accumulate, so if we've got some big gap between where we are and where we want to be, and that persists for a long period of time, we should adjust by sort of ramping up our control. And the way we perform that is by adding together all of the errors over time, right? If you remember like Riemann sums, yeah, thank you, Matthew. If you remember Riemann sums, like we're doing the same thing here, right? We're approximating an integral by adding up all of our errors, right? And then we add this to the original proportional controller. So we add this term, ki times integral of e. That should really say dt. Oh, well, doesn't matter. It's supposed to be integral with respect to time. Sorry about that. So ki times integral of e with respect to time, right? And so now we've got two constants. We've got this kp from earlier and this ki, right? And we can tune them together. So just to recap, I think you guys should think about which cases you might want to use integral controllers. That'll probably come up in the discussion. And then think about the problems. Well, we've got the problems right here, or some of the problems. In general, integral controllers are much more likely to overshoot, right? So they make that part worse. They make it so that you're more likely to follow some path that eventually leads above the, like that eventually pushes you above the target or past the target, right? And that's because, well, it's got no notion that, I mean, if we go here, right? If you are the Brown controller, right, you're going to have still summed up all of this, right? And then by the time you get here, right, you're still going to have this big integral term, right, that's got the sum of all of these errors. So you're still going to be pushing harder, right? And you're going to push farther for a little while, right, until that integral term balances out, right, with, or that integral term goes to zero when summed with whatever is here, right? Yes, U is the power that you're going to be putting into the motor. Remember that U is, we call that control input, right? That's the letter for control input. You'll see that pop up all over the place in controls and in motion planning. Spoiler alert for the end. So PI controllers are still not ideal. They overshoot. We also have this issue that comes up of integral windup. The long and short of it is that your system is suddenly no longer sort of memoryless, right? It suddenly has, or your controller rather, sorry, has some sort of memory, right? Which can be good for the situations that we just described, but it also can make it a lot harder to actually debug and tune and make sure it works for all situations, because it's going to matter what happened in the past for what happens now, right? Even if we have perfect state estimate and everything, it's not just the state that matters, it's what happened prior to this point in time. So yeah, we're adding another state variable essentially into our controller, right? And that's not coming from physics, that's just coming from how we write up our controller. The concrete scenario, right, is that like if we get stuck on a rock or something, we'll say URC, right? If you get stuck on a rock for a little bit and you've got an integral controller, that's going to all add up, and then eventually we're going to break free of the rock, but we don't necessarily want to apply that integral anymore. So it's going to still be there even though we don't need it, and it's going to take a while for it to go back down. So to combat this, we add another term called derivative, and you can see the terms taking shape now, right? Proportional, integral, and derivative. And that's just a constant times the derivative of your error. So the intuition here is that if your derivative is changing really, really quickly, right? If that means that you are approaching your goal or you're approaching your goal very, very quickly, right? You want to slow down so that you avoid overshooting the target, right? And we just write this as the derivative of error. And you can't usually use derivative on its own. Usually you're going to actually use proportional derivative or proportional integral derivative, right? Same goes for integral controller. You don't want to just use an integral controller you usually want to combine it with proportional. So now we've got this magic thing called PID that can give us a lot of neat things. And as a quick recap, just of what each of the terms do, and you may want to remember this, proportional is what actually drives you to the target. Integral is what makes up for any long-term gap that you have, and you can think of that as compensating for errors in your model, right, or in your tuning. And then derivative is what avoids overshooting the target. And together, these three terms come together to make a controller. So is derivative always going to be VE? What's VE in this? Oh, sorry. Yeah, that makes a lot more sense. So derivative. Okay, let's go back. So if your error is increasing, your derivative term will be positive. If your error is decreasing, your integral term will be negative, or your derivative term will be negative. Yeah, sorry, I just did not get what you're saying there. My bad. It basically just acts in the opposite direction of the system's velocity to slow it down, if that makes sense. So the integral, so somebody asks, is the integral being taken over the past n seconds, for example? So usually you'll actually take the integral over the past infinity seconds, basically from the time that you started to now, right? Integral from 0 to time t. And the reasons for this are a little bit more complex than there are a couple of them, but a little bit more complex than we can get into right now. Essentially, it ends up making it a linear. Okay, the math term is it ends up making it a linear system with like fewer states. If you take the integral over like a finite amount of time, it adds a lot more complexity. Actually, unintuitively, it makes it much more complex both to compute and to analyze the system. So we don't usually do that. We usually take the integral over all of time. You'll notice that all of these curves that we've been looking at, all of these things, look basically the same, right? In some way, they're sort of exponentially approaching the target. That's not a coincidence. For anything that's a linear system, the response will always be exponential. What is a linear system, you might ask? That is a very good question, but it's not something that we're going to cover in depth here. Essentially, the idea is if you add together the states, or if you add together two inputs if you add together two responses of linear systems, the result will be a valid response. That probably does not actually give you any intuition. So let's see. I guess another example is if you multiply the control input by 2, right, your output will be multiplied by 2 as well. So if you give it twice as much voltage, you'll go twice as fast. There are a couple of other conditions for a linear system as well, but that's sort of the easiest one to describe. Anyway, all systems of that type are going to respond in an exponential manner, right? They're going to respond either exponentially decreasing, right? So exponentially approaching some asymptote. That is good. That means that your system is stable. And then it also could be exponentially increasing, which is bad. That means that your system is unstable. So our goal as engineers is to try to get a system that is decreasing, right? Another question that you might ask, well, exponentials can't overshoot. There's a technicality here. The easiest way to rectify this is just to say, okay, everything is some combination of an exponential and a sine wave, right? So like instead of just being so everything is e to the at, but not actually, it's actually like e to the at times sine of x, right? Or possibly times sine of x, right? Sine of bx, we'll say. bt, we're using time. But That's actually still technically an exponential because of like Euler's formula. Again, not going to go into that. This back half of this presentation is going to be a whirlwind. So be prepared for me to throw a lot of things out. Yeah. Okay. Let's speed run. Oh yeah, sorry. Somebody asked, so is a Fourier transform a linear system? The Fourier transform is a linear operator. It's not a linear system in and of itself. It's not a linear system because the Fourier transform isn't a system, right? It doesn't have a physical analog, first of all, but it also doesn't really have state in any meaningful way. I guess you could consider the Fourier transform a system in a way, but usually you wouldn't consider it a system. So it is linear, yes, but it is not really a system. Sorry, just addressing a question in the chat. Okay, so we're going to do a speed run of all of the control stuff right now. This is going to be really fast. It's not going to be in depth at all, but it's going to hopefully give you an overview of what, if you work on control stuff, what you might end up working on. So I've got my little subtitle here. Let's speed run 2 upper division classes and a grad class. Let's go. By the way, if you're curious, those classes would be 3550, 4550, and 6550, I believe, in the EC department. Okay, so remember we talked about motion planning. There are things that you can do for motion planning that help controls. Remember that a lot of the things that we've looked at have been something called a step response, which is where you jump up, right? You instantaneously change your reference or your goal from like 0 to 1000, right? In general, your system can't actually do that. Your system really can only do smooth changes. So we can, if we plan our motion, right? If we plan it out ahead of time to be something that the system can actually do, we can often accomplish much better or more precise control. This is especially useful in the case where we're trying to like drive a set distance, right? If we're trying to drive 1 meter, we shouldn't tell our robot, okay, right now we should be at position 0, and then, okay, our goal changed to 1 meter, right? Our goal, so suddenly our error is 1 meter. We need to be 1 meter from where we are now, and you're doing a bad job, fix it. And the reason we don't want to do that is because that means that suddenly you are going to apply like full voltage to your drivetrain, right? And that voltage is going to saturate. You're going to cap out because you can't actually apply 10,000 volts to your robot. We don't have that kind of electrical system. So it's going to saturate at like 12 volts or 24 volts or whatever your amount is, which inherently makes your system very difficult to work with. It makes it no longer a linear system, right? If you double the control input, it's still just going to be capped to the same value, so you're not going to get any different output, right? And as soon as it's not a linear system, basically because you can't multiply your input by 2 anymore, right? So it's not a linear system, and that makes it much more complex to work with. So the long and short of it is that smooth motion set points make PID and control systems in general work a lot better. We can do something called trapezoidal motion, which is a very common scheme for trying to move in a straight line, which is where you try to limit acceleration instead of just having this big step up. So you'll accelerate to some maximum velocity, right? Then you'll stay at that maximum velocity. Then you'll decelerate back to 0 velocity, right? And this can be very, very effective when you're trying to do smooth linear motion, essentially. And we actually use variants of this for how we plan to move along paths often, right? So if you've got a path, again, harkening back to the motion planning lecture last week, we've got, you might have some path that you're trying to follow. You might want to parameterize that or drive along that by limiting acceleration and limiting velocity, and then so basically applying this sort of trapezoidal profile to it. So this has a lot of benefits. You're more precise. You have an easier system to control, and you put a lot less stress on your robot. Okay, more stuff. There's this idea, so that we sort of briefly mentioned at the beginning, where if you understand the model, it is much easier to do good controls. What this comes up to in the real world is often something called state space control or state space modeling. And state space modeling is where you model your system based on sort of this differential equation. So you write a vector out of your state, right? And this is the math vector. I'm sorry about the terms. This is a math vector, right? Which means it's just a fixed collect. I guess it's n different real numbers, right? So in this case, x would be in R2. It would be a two-dimensional vector, and it would just be position and velocity, right? And that would describe the state of the system. If we were working with a Robocup robot, this might be x, y, theta, vx, vy, v theta, right? That might be the state of our robot or something like that. And then we're going to write out something that describes how that state changes with respect to control input and with respect to what it is now, right? So, for example, in the case of position velocity, right, if you just have an acceleration that you apply to the velocity, that might be, well, the derivative of with respect to time of this first component is going to be equal to the second component, right? And then the derivative with respect to time of the second component might be equal to this u, this control input, right? And that's just where, if that might just be the acceleration that we're applying. For systems that are very simple, you can write them, and for systems that are linear, you can write them like this, where A and B are matrices. You might now be starting to understand why it's a linear system, or at least understand that it has something to do with linear algebra. Linear algebra will show up a lot in controls in general, and in motion planning, and in robotics in general. Yeah, linear algebra is a useful class. So for some systems, you can write them as linear in this form, ax plus bu. For other systems, you might have some nonlinear force or some nonlinear dynamics that keep you from writing it like this. Those systems are harder to control. For anything that's linear, we actually tend to have very simple ways of, well, quote unquote simple. They still require a lot of math, but simpler ways and more sort of plug and play ways to generate controllers. So yeah, modeling lets you do a lot of cool things. It lets you simulate your system so that you can test not on the multi-$1,000 robot, but on a simulation. You can make sure that things are mostly correct, and then you can plop it on the robot. It also lets you define an optimal controller. This is sort of similar to the LQR thing that we talked about last week. Don't worry if you don't remember it. Basically, what this means is it lets you define a cost function, and then it lets you design your controller such that it's the best possible controller that achieves the lowest possible cost given that cost function. And then you can also do something called model predictive control, which we'll talk about in a second very quickly. Again, this is like a speed run. Don't worry. It's a lot of information real quick, just to get you comfortable with like some terms. So this is like an example of the Robocup state space, right? I think we already talked about that, so I'm not going to go over it too much again. Okay. Another thing that you can do when you have a model is you can do filtering. We're going to talk about this a lot in a later week, I think week 5 or 6. But you can actually use your model to get a better estimate of your state. And you can do this by predicting, right? So if you know that you are here right now, and you believe that you're going to end up right here based on your model, right? Say this is a robot drivetrain. But then maybe you get some sensor measurement that says that you're here. Let's say that's GPS, right? Well, you know that GPS isn't perfect, but you also know that your model isn't perfect. So the reality is likely to be somewhere in the middle. And that's this entire field called estimation or called filtering, right? You can use the same technique to predict velocities, positions, and other things all at once. You can use it to combine measurements from multiple sensor inputs, right? And to weight those together. You can use this in some very interesting ways, which is why it will be a later topic for this. Okay. And then we've got this thing called model predictive control, which is very similar and actually almost identical to some of the motion planning stuff that we talked about, where you are, if you remember from last week, maybe you don't, because we went over it fast last week too. But there are types of motion planning algorithms where you have some cost function, right, that defines how good a particular trajectory or a particular plan is, right? And then you try to optimize that cost function. You try to find the best possible cost function. MPC actually does the same thing. So if you have this model, right, you're able to, based on the predictions that that model gives, you're able to find out what the trajectory will be if you have a certain sequence of control inputs, right? And then using that, you are able to find the best possible control input that makes the best possible trajectory. Usually what this cost function will be is like, closeness to a reference trajectory. So in this example, right, we've got this trajectory, right, is the past, right? This is our past. We want to follow this red trajectory, right, which means we want to minimize this error, right, this error between them. And we want to do that by driving this one up towards that red trajectory. So we can do this by basically saying, okay, if I have this sequence of control inputs, I will do this, right? I will follow this trajectory. And I want to manipulate this sequence such that I get the trajectory that ends up the closest to that reference trajectory. And then the idea is that you take one step of this, right? And then you replan. So you repeatedly plan out to all the way to some time t, right, in the future. You plan that out, you take one step, and you replan. Something I did not discuss here is how you actually find the best possible sequence of controls, right? I sort of hand waved that away. That is something that you need you need an optimizer for, right? You need something that basically just gives you the best possible sequence of controls given that. There are a lot of ways to generate that, and I am not going to discuss them here. Some of those are just off-the-shelf solvers where, like, if you just give it an equation, it will optimize it. We use those a lot. Somebody asked, is this like pure pursuit? In a way, yes. If you have used pure pursuit for differential drivetrain robots or for Ackermann drivetrain robots, basically for car-like robots, this might look a little bit familiar. The idea of pure pursuit is that you make a plan and then you follow a step of it and then you replan. So in that sense, pure pursuit is sort of a type of model predictive controller. Usually with model predictive controllers, we define what the plan is by an optimization function rather than by a fixed curve. So like pure pursuit, right? Pure pursuit is sort of a heuristic way of doing a plan, right? Whereas model predictive control usually talks about finding the optimal plan and then executing the first step of that. But the core algorithm where you plan, take a step, and then replan, the core algorithm of that is basically the same as what it looks like in pure pursuit. Okay. I've got a couple of secrets to share with you. These are not actually secrets, but like they're good things to know. I got a little loopy by the end of these slides. So controls and motion planning are basically the same thing. In practice, a lot of people, especially in the industry and especially in the field of robotics, and even more especially, if I jump back here, you'll notice that this is like sort of a complex thing to do, right? We have to do this whole motion plan, and we have to do it in a 1/100th of a second, or however often we're running our control loops, right? So it takes a lot of computational power. Recently, we have actually achieved the computational power needed to run this in real time on robots, right? Previously, it was restricted to like systems where you don't need to run it 100 times a second, like chemical plants, right, where you might only need to run it once a minute, or something like that. All that to say, motion planning and controls are very intrinsically linked, right? These days, people often use model predictive control as a motion planning method and a controls method all in one, right? You can also note that you're allowed to have multiple levels of controllers. So you could have one controller that calculates the target velocity, and then another controller that uses that target velocity, like tries to follow that target velocity, right? Using that as a reference to calculate voltage. right? Those are like things that you can do. So you can layer your controllers together to achieve more complicated control architectures. So yeah, controls and planning, basically the same thing, or at least very closely related. Controls and then estimation, which is the problem of trying to figure out what that state X is from whatever sensor measurements you get. Those two problems are like literally the same thing, or literally two sides of the same coin, we'll say. There's this big mathy theorem that says that they are what's called dual problems of each other. You can just think of that as they are the same problem, or at least they're very similar problems. And here you can see the part where I got a little loopy. Wow. Duality. Yeah, that's a mathematical term that, like, if you have any friends who are math majors, or you are a math major, they may throw that around occasionally, and now you may know what that means. All right. That's all I had for this lecture discussion section. Does anybody have any questions before we jump out into breakout rooms? I'll stop sharing my screen and put my camera back on. So yeah, does anybody have any questions? Give it 1 second. All right. If nobody has any questions, I have one more thing for you, which is the classroom link for this week. The link is just going to be implementing a simple PID controller on a particular system. I think don't worry about it too much if you are still struggling, or if you're sort of you're worried that you're falling behind. I think try to prioritize some of the ROS exercises. But if you have time and want to do some control stuff, that is a exciting, fun exercise for you. Okay, I'm going to stop the recording, and we are going to hop out into breakout discussion sections.